Linear transformations. Alright, one way to view AX equals B, our normal linear system, is it's a matrix equation, it's a system, or it's a vector equation. All these things mean the same thing to me. But let me add yet another way to think about this. That way is we have some vector x. Now this object, this matrix A, is actually, you can think of it as a function. And when I write AX, the result of this is this vector B. So A acts on X to result in B. So this is just like when you first learned about functions in, I guess, 8th grade. You have some number X, you take a function F, and you act on it. And the result is some Y. So for instance, if my function F from the reals to the reals takes a number X and squares it, then that means F takes an X and outputs an X squared. So I can do something very similar here, where I take a value X, a vector in this case, act on with A, and I'll get B out of it. So a transformation is a function from Rn to Rm that assigns to each vector in here a vector over there. Well, you know what that is. It's nothing more than a different definition of a function. So they're essentially synonymous for us right now. Now, going back to old school terminology, this part of our function definition, this is the domain, and this right here is our codomain. You might know this as the range. I avoid that terminology because it's often confused with something else. So I will exclusively use codomain, and I encourage you to do so too. That's the modern terminology. The set LRN is what we call the image. Now, this is where I say it might be confusing. Some people call it the range. I will call it the image. That's the standard terminology right now. So, for instance, let's say I have the rule F going from R to R. Well, and it's defined by X goes to X squared. The domain of F, well, what are all the values of X that we can use? Well, as I say here, it's R. The codomain of F, well, that's also R, as we can see here. Now the image of F, those are all the values, so the image of F, which I've written here as this, so I can write this as F of R. So it's almost as if I take every possible real number and I plug it in for my rule for F. Well, if I do that, what do I end up with? I end up with the non-negative reals. So what you should really notice is the image is always a subset of the codomain. They could be equal, but it's at least a subset. Alright, so let's do an example of this that is not based upon one variable functions, but a linear function like this. So I define a matrix A as so, and I give you these three vectors. Now I define a transformation L from R2 to R3, and I define it by saying the linear transformation L operates on a vector X inside of R2 by saying do this matrix product AX. Well, I spell that out for you right here. What is AX? Well, this is A, and this is some arbitrary X. We learned in the last section that this can be rewritten in that manner. So, in other words, L applied to X is going to equal x1 minus 3x2 3x1 plus 5x2, and negative x1 plus 7x2, like so. All right, so the first step is determine LU. So that means I'm going to plug in 2 and negative 1 for x1 and x2 respectively. Well, 2 minus 3 times negative 1 is 2 plus 3, which is 5. Next up, 3 times 2 is 6, and 6 minus 5 is 1. And then negative 2 and 1, or negative 1 plugged into there. Negative 2 minus 7 is negative 9. So that right there is L applied to the vector U. Number 2, give some vector x star in R2 such that it maps to B. So I need x star such that Lx star equals 3, 2, negative 5. Well, L applied to x star can equally be viewed as A applied to x star. All right. Looking at this, we see that we are really trying to solve a matrix equation. We're asking, is this vector here in the column space of A? Or we don't know the terminology yet, but is this vector here in the span of the columns of A? Okay, well, how did we figure that out? Well, let me write this out. Is 3, 2, negative 5 in the span of the columns of A? Now we learned that by taking this augmented matrix and seeing if it's consistent or not. Okay, let's do that. Well, A is 1, negative 3, 3, 5, negative 1, 7, and B is 3, 2, negative 5. We row reduce this, which I'll do right now. And by Jove, yep, we have a solution. Namely, if I set x star equal to x1 star, x2 star, then I'd have 3 halves, negative 1 half is a solution. So there's my x star. So that is the answer 2. Number 3. It asks, is x star unique? Well, to determine if x star is unique, we need to find if there are any solutions to ax equals 0 that are non-trivial. So a non-trivial solution to that gives more than one solution to ax star equals b. Now this is where some confusion is going to happen. You're going to say, well, look, there's a 0 row. Therefore, we have a free variable, yada, yada, yada. That is not the case here. We only have the trivial solution. Now, to hammer this home, let's look at ax equals 0, like I promised. If you stop and think about it, taking the augmented matrix A with 0 and taking its reduced echelon form, I'm going to get 1, 0, 0, 1, 0, 0, 0, 0, 0. I get the same reduced echelon form here for the coefficient matrix that I would over here. It's just the right-hand side of this vertical bar stays the same as a 0 the entire way through. Now from this, let's think about it. We have A, x star I'm writing as x1 star, x2 star. So I see that I have indeed two variables here. what do those two variables represent? Well, A is comprised of two columns, A1 and A2, say, and then I have x1 star and x2 star here. This matrix product equals x1 star, the scalar, times the vector A1 plus x2 star times the vector, A2. So we see that we do indeed only have two variables and hence two weights here. So there is not a free variable despite the fact that we have a 0 row. So be careful with that. So is the solution unique? Yes. The solution is unique. And then finally, is C in the image of L? All right, let's zoom back up here. We have C, doing number 4, equals 3, 2, 5. All right, see if this is in the image of L. So if C is in the image of L, well, then there exists some x such that Lx equals C, right? Because that means if it's in the image, I could use some element from the domain and map and get to it. All right, notice this is nothing more than the previous question asked again with just a different vector in place right here. Now, we know Lx is really what? Ax. And so we're asking about the consistency of this system. Well, 1, -3, 3, 5, -1, 7, 3, 2, 5. That's what we're looking at there. What do? As usual, reduced to echelon form, which is boom. What do we have going on over here? We have a pivot in the rightmost column. Therefore, this is an inconsistent system. So there's no solution. So, what does that mean for us? Is C in the image of L? Nope. So, therefore, C is not in the image of L. All right, next up. A linear transformation P is given by this particular matrix. So what do I mean by that? I'm saying I have a linear transformation P, which acts on X by doing 1, 0, 0, 0, 1, 0, 0, 0, 0 times X, which is X1, X2, X3. Now, what does P do? What is the rule for Px? Well, I've already started to establish that here. It is nothing more than taking each one of these columns and tacking on its weight. So that's going to be x1, 0, 0, plus 0x2, 0, plus 0, 0, 0, which is x1, x2, 0. So what P does is it basically strips off the x3 and leaves x1 and x2 as they are. What does that mean to us geometrically? All right, think about that. x1, x2, x3, that's something in three-dimensional space. So I have some arbitrary vector x sitting here. It's got coordinates x1, x2, and x3. What this does, if I call this x and this y, or really x1 and x2, because we're using x1, x2, x3, it's going to project it down into the x1, x2 plane. So this projects x into the x1, x2 plane. Now, what's the result of p squared x? So what I've done then is I've taken px, which I know is just x1, x2, and 0, and I'm saying let's apply p to that again. So p of px is going to be 1, 0, 0, 0, 1, 0, 0, 0, 0, applied to the px, which I know is x1, x2, 0. Doing the same thing with my vector equation decomposition above, right there, I say, all right, that's x1, 0, 0, because that weight goes to that column. This weight here goes to the second column. And the 0 weight goes to the third column. And lo and behold, I get x1, x2, 0. So what does p squared do? Or what does p do to the image of px, or x under p? It does nothing. So think about that geometrically. It's common sense. I have some vector here. I project it down to the x1, x2 plane. If I already have this vector sitting in the x1, x2 plane, and I project it again, is it going to go anywhere? Absolutely not. If you're having trouble visualizing that because of the third dimension, just think about it in 2 dimensions. I have an arbitrary vector x here. Let's say I project it down to the x plane, or x line, x-axis here. That's the x1 and x2 here. Now, if I project this again onto the x1 axis, what's it going to do? Well, it's going to stay the same because it's already resting on the x1 axis. All right, what we're going to do now is specialize our notion of a transformation. We're going to say it's linear if, when I apply that transformation to a sum, it's as if I apply it like so. So in other words, it distributes. And if I happen to have a scalar times my vector here, I can just pull that scalar out as I see fit. All right. Now, every matrix transformation turns out to be a linear transformation. Think about that. A applied to a sum x plus y, well, what is that? That's ax plus ay. And if I have a times some scalar alpha x, then I can pull that alpha out and do ax. So this is nothing more than what we already know. Okay, now not every linear transformation is a matrix transformation. So just because I can craft up some L, it does not mean there is a matrix that represents L. Okay? So just bear that in mind. If I give you a matrix, then I can think of that as linear transformation. But if I give you a linear transformation, that does not mean that I can come up with a matrix for it. All right. What are some examples of linear transformations? Well, I've already discussed one. Matrix transformations. Another one, this is a kind of interesting one, and this is a hint. What about the derivative? If I take the derivative of a sum of functions, well, is that the same thing as that? And we also know and love the old constant rule. So if I had CF, well, that's C times the derivative of F. And you can probably guess that the integral is another linear transformation. Now, what are some properties of linear transformations? Well, first off, they preserve 0. All right, let's see why that is true. Take some arbitrary x. Then L of 0 is the same thing as L of x plus negative x. I'm just rewriting 0 in a funny way. Well, what's that equal to? That's Lx plus L of negative x. Now, negative x is negative 1 times x. So that's Lx plus negative 1 Lx, which is, of course, going to cancel. So L of 0 indeed equals 0. And they also respect linear forms. This right here, if you think about it, I use it right here. It's just using both the properties at once. I'll let you all prove that on your own. Alright, here's a very important example of a linear transformation. It's called a homothety. Now that's a map that takes something and maps it to a constant multiple of itself. Alright, now we say a homothety is a dilation if lambda is bigger than 1, and it's a contraction if lambda is between 0 and 1. Okay, let's think about that. Let's say my map takes a vector x and maps it to 2 times that x. Well, what's this map do? It's nothing more than scalar multiplication. What's scalar multiplication do? It either takes my vector and makes it longer or makes it shorter. It could also throw it in the opposite direction, but we're going to ignore that case for now. So that's all this thing is doing. And you can think about it, if lambda is bigger than 1, in other words, this number here is bigger than 1, it's going to increase the length of my vector. Therefore, it dilates it. In the same way, if I pick some constant between 0 and 1, like 0.3131131, obviously, then what's that going to do to the vector that I hit it on? Well, it's going to shrink it. And so, it's going to contract it. Now, homothety is a linear transformation. That's my claim here in this theorem. Well, in order for that to happen, as a theorem, there better be a proof. I challenge you to do this on your own right now. And if you have trouble with that, we will discuss that in class. Alright, the last thing. I have a transformation here. It takes a vector x and it hits it with this matrix A here. So that the result basically flips the entries in my vector and negates it at the same time. It negates one of the entries. Now my claim is this is a counterclockwise rotation about the origin by pi over 2 radians, or 90 degrees. Alright, so what I'm claiming here is I have some arbitrary vector x. If I take this vector x and I hit it, let's call this R. Let me change colors. This vector here is Rx. Alright, let's prove this. So let's see here. This is x1, x2. Now I can draw this like so. So this length right here is x1, and this length right here is x2. This right here is negative x2, x1, is the image of x1, x2. Let's call this little angle here alpha. Now if you think about it, if I draw this right triangle to the y-axis instead, that's the key step here, then this little distance right here is x2, and this distance right here is x1. So notice the distance is x2, but when I actually use like sine and cosine, I keep the sign negative. Alright, now looking at this triangle here, I see that alpha corresponds to x2 over x1, and I have x2 over x1 here, so this is also of measure alpha. Now the complement of alpha, let's call that beta right there, would also be the complement of beta there. Let's grab another color. this right here is the angle we need to show is 90 degrees. All right, well, that is a really bad hypotenuse, or potential hypotenuse, I should say. Anyways, alpha plus some mystery angle delta here, what do those have to add up to? Well, they form the first quadrant. So this must be the complement of alpha, which we know to be beta. Well then, by that same token, if beta is the complement of alpha, then this red right here must be alpha plus beta. And therefore that's 90 degrees. So there we go.